last but certainly not least, so I'm very happy to introduce our first speaker, 16 Chen from NYU.
Thank you. Okay, so good afternoon, everyone. I'm Chen, and I'm a PhD student working with Marcelo Matar at NYU. Today, I'll be presenting a project about modeling human planning. So as humans, we use planning to solve everyday problems. For example, we use maps to plan our routes, or when we play board games, we plan our moves to win the game. And these problems can be abstracted into a decision tree. Here, each circle represents a state, and each arrow represents a transition. To plan our actions, we need to mentally simulate future outcomes to find a path to reach our goal. So a key question in planning is, how do humans decide what to simulate and why? The classical approach to this problem is to model human planning using choice data. So usually we have a carefully designed task, or we collect massive data sets in complex tasks. And in either way, we define a series of computational models, we feed them to the choice data, and we do a model comparison to see which model better describes the data. And this approach is generally effective, but it strongly relies on the assumptions we build into the model. And in many cases, there exist certain models that can better describe the data, but are just not considered. In this project, we want to try a more flexible modeling approach. So instead of pre-specifying models, we want to build an agent that can learn to plan. We want to impose minimal assumptions on what planning strategy the agent can learn and let it discover a strategy itself. And we want to see if it can learn to plan like a human. So we use an eye-tracking planning task developing our lab. In this task, participants are shown with a decision tree with 11 nodes arranged on a circle. So the blue node here is the starting state, arrows represent transitions, and each node is associated with a point indicating the reward of getting there. So participants move their mouse to click to navigate between states, and their goal is to maximize cumulative reward. In this task, both points and arrows are randomly shuffled every trial. Those points are sampled from a distribution centered on 0. Every trial has a 15-second time limit. And importantly, the point in a node is only revealed when participants fixate on that node. So here's an example trial. The red dot here shows the gaze position, and later the black dot will show the mouse position. So we can see that participants generally use their fixations to search over the decision tree. They often search forward and explore different branches of the tree. And sometimes they also jump backward. And once they've determined their mind, they will move their mouse and click on the path to choose it. With this setting, gaze trajectory is strongly coupled with states participants are considering. And as an example, trajectory shown on the right, the trajectory clearly shows how they search over the decision tree. In general, participants perform these tasks quite well. They fixate about 9 times per trial and choose the optimal path on 63% of the trials, earning 75% of maximum reward. So before diving into people's behavior, we first consider 2 representative strategies, and both widely used to model planning. The first strategy is A star. So A star is a tree search algorithm, and it expands nodes based on path value. So for example, let's say we have a search tree like this, and we want to choose which node to expand next from the 3 purple candidate nodes. And in this case, A star will compute the path value of a candidate node, which is the cumulative reward of the path leading to that node. It does so for each candidate node, and it expands the node with the highest path value. Also, A star always expands new node in the task, so it doesn't naturally revisit node. Okay, and the other strategy we consider is rollout. So rollout is a search algorithm that is based on forward simulation, and it is the basis of Monte Carlo tree search. It simply simulates one path at a time, starting from the root. And in many versions, rollouts also tend to revisit nodes with a higher future value or Q value, which is the cumulative future reward expected from a node. So for example, suppose we are going to decide which node to visit next between B and E, and we compute their Q value, and we found that the Q value of E is higher than B, then the algorithm will tend to visit E. So now we have two strategies that give different predictions. A simple question we can ask is, do people follow A star or rollout or just something else? So we first look into where do people fixate in general. If we separate saccades by whether a saccade goes to a child, the parent, or the sibling, we see that a saccade very often goes to a child, and sometimes to a sibling and to the parent. This suggests that people are doing local search, and this is generally consistent with tree search, but it's not consistent with rollout because rollout will not visit siblings. And we then look into the distribution of fixations across different depths. We see that people generally fixate less on nodes deeper in the tree, and importantly, they fixate more than once on depth 1 node, suggesting that they do refixate nodes. And this is consistent with the rollout, but inconsistent with A star because in this task, A star won't naturally predict revisiting a node. So with these simple examples, we see that neither algorithm fully captures the fixation pattern very well. Then how should we model the strategy here? So our approach is to build a task-optimized recurrent neural network. So the agent is a recurrent neural network with an actor-critic architecture, and it interacts with the decision tree environment, gets input from it. So the input include the identity of the fixated node and its point, the identity of its parent and children, as well as the node the agent is currently in. So this setting matches the local visual information participants get when they fixate on a node. And at each time step, the agent chooses to either fixate on a node or make a move. If it chooses to fixate on a node, it moves the fixation pointer to the target node. And if it chooses to act, it makes a move and transits to the next state. So the agent is trained under a meta-reinforcement learning setting using politic gradient methods. So following the standard meta-reinforcement learning practice, the weights of the agent are frozen within an episode. And instead, the agent must adapt to a new environment through its recurrent dynamics. So in this case, the planning algorithm is implemented in the recurrent dynamics, and the planning here can be viewed as a kind of fast in-episode learning. Across different episodes, the agent is trained on a distribution of environments, so it can learn to extract the right inductive biases and meta-learn a generalizable planning algorithm. So the goal of using meta-reinforcement learning here is to learn a planning strategy that can effectively solve the task given the constraints intrinsic to the recurrent architecture itself. So to see the agent, to see if the agent learns a human-like strategy, we compare its behavior with human fixation behavior. So we first see that the agent shows a very similar local search pattern, suggesting that it learns to do tree search, and this is generally consistent with A star. And then we check which frontier node is favored for expansion. Specifically, A star tends to expand the frontier nodes with high path value. And we see that the fixation probability increases with path value in both humans and the agent. And this means that as predicted by A star, both humans and the agent tend to distribute more fixations to exploring promising paths and use their resources more efficiently. Okay, so we see that search is guided by path value, but what about Q value? So suppose the current fixated node has two children, child 1 and 2. And in this case, rollout tends to revisit the child with higher Q value. And surprisingly, we'll also see that in both humans and the agent, the probability of visiting a child increases with the relative Q value between the two children. And this is consistent with the rollout, but not with A star. And the effect here suggests that as predicted by rollout, both humans and the agent tend to revisit nodes that have been found to lead to promising future outcomes. And finally, we ask when humans and agents do not fixate a child, where do they jump to? So here I show the proportion of jumps to each of the depths, and the dotted line here are chance levels. So we see that both humans and agents have a strong tendency to jump back to depth 1. And this is consistent with the idea of jumping back to the root to start a new rollout. Okay, so what have we learned so far? We've seen that the strategy of humans seems to be a hybrid of A-star and rollout. It has features from both. Consistent with A-star, the strategy does local search and is sensitive to path value. Consistent with rollout, the strategy is sensitive to Q-value, and it often jumps back to depth 1. And surprisingly, the task-optimized recurrent neural network model can capture this hybrid strategy. Okay, so how do we make sense of these results? Why do we even see rollout-like behavior? One hypothesis here is it's because rollout is memory efficient. So specifically, rollout only need to keep track of one path at a time instead of maintaining the representation of the whole tree. So it requires less memory. And if this is true, then it will predict that imposing memory constraint will lead to more rollout-like behavior. So to examine this, we simply adding noise to the hidden state of agent to constrain its memory, and we check the two predictions from rollout. And we see that with higher noise in its memory, the agent more often revisits children with high Q value and also more often jump back to depth 1, suggesting that it behaves more like a rollout. And this confirms our hypothesis that memory constraint is an underlying reason for rollout-like behavior. Next, we will dive into the mechanism and ask how the agent actually solved the task. We start by asking how each fixation changes the policy. We predict that fixating on a node changes the probability of selecting that node. So specifically, fixating on a good node will increase the probability of choosing it, and fixating on a bad node will decrease the probability. And this is exactly what we see. The policy changes after a single fixation, and it increases or decreases depending on the reward. So we know that the agent uses individual fixations to dynamically build its future policy. And further, we know that in planning, simulating a node should not only change the policy of the node itself, because once the information is backed up along the path, it should also change the policy along the whole path. So here we show how a single fixation changes the policy along the path. We see that fixating on a node changes not only the policy of the node itself, but also the policy along the path, including the parent's parent, and so on. And from this observation, we know that the agent represents a node through its path trace, and it uses this representation to perform value backup. Okay, to summarize, we built a meta-reinforcement learning agent on a planning task, and we found that the agent learns a planning strategy that closely matches human strategy. And this strategy has features from both A-star and rollout, but seems to be not identical to either of them. And we also show that the underlying reason for this hybrid strategy might be that the agent tries to efficiently solve the task subject to its memory constraint. Okay, with this, I want to thank my advisor, Marcelo, my collaborators, Fred and Srijan, as well as the lab. And finally, another advertisement. Fred will join Dartmouth College as an assistant professor of the cognitive science program in fall 2026, and he will be recruiting PhD students, postdocs, RAs. Fred is definitely one of the most brilliant collaborators and mentors I've been working with, so definitely contact him if you are interested. Thank you.